In this video, we're going to review the 4 gas laws. The important thing to remember here with these laws is that we are never changing the amount, the number of moles, or the mass of the gas that's involved. Before we look at those gas laws, let's just review the Kelvin scale because it's very, very important that you remember to convert all your degrees Celsius to degrees Kelvin. And you do that by adding 273 to your degrees Kelvin. So in our example here, we're going to convert 20 degrees Celsius to Kelvin. So we're going to do 20 degrees Celsius plus 273, and the units would be kelvins per degree Celsius. We don't usually write that. We usually just write down our answer, which would be 293 Kelvin. So let's make sure that we are always converting our temperatures to degrees Kelvin. So now let's gas laws. So here's Charles's law. Charles's law shows us the relationship between volume and temperature. And so if we remember our gas, what we've learned about gases, if we increase the temperature, they are going to move around more. They're going to spread out more. So we should be noticing a trend that as the temperature increases, the volume increases and vice versa. So in this example, it says a certain amount of gas occupies a volume of 60 liters at 27 degrees Celsius. What temperature is needed so that the gas has a volume of 100 liters? So our V1 is 60 liters. Our T1 is 27 degrees Celsius. We're going to add 273. We never ever want to use degrees Celsius. So we have 300 degrees Kelvin as our T1. And we're looking to get to 100 liters. And we want to know what temperature. So if we're increasing the volume, we should get a higher temperature. So we can kind of make that known in our brain, and then hopefully we can prove that to ourselves and get a higher number. So our formula is V1 over T1 equals V2 over T2. That formula rearranged is going to look like this. And then we can put our information in. So we have 100 liters, 300 degrees Kelvin, divided by 60 liters. So our liters will cancel, and we get 500 degrees Kelvin. So that makes sense. We have a temperature that's higher, which makes sense for allowing for a larger volume. The next gas law we're going to look at is Boyles Law. So Boyles Law compares our pressure and our volume, keeping the temperature constant. So again, if we think about our gases, if we give them less space, so reducing the volume, those gases have less space to move around. And when they're moving around, they're bouncing off the walls and they are changing the pressure. So if we decrease the volume, we are increasing the pressure. Okay? So let's look at an example. A balloon with a volume of 2 liters is filled with a gas at 3 atmospheres. So atmospheres are just another unit of pressure. Usually we use kilopascals, but atmospheres are fine too. So if the pressure is reduced to 0.5 atmospheres without a change in temperature, what would be the volume of the balloon? So we have V1, 2.0 liters. We have P1, 3 atmospheres. We have P2, 0.5 atmospheres. And we're being asked to figure out our volume. So we're decreasing the pressure here. So that means we're actually going to be allowing those gas particles to move a little bit more freely. So we should get a higher volume. So our formula is P1V1 equals P2V2. And if I rearrange that for V2, it would look like this. And then we can put our information in. So we have 3 atmospheres, 2 liters over 0.5 atmospheres. So the atmospheres will cancel. We'll be left with a unit of liters, and we get 6 liters. So that makes sense. We have a higher volume because we have a lower pressure. The next law is Gay-Lussac's law, and Gay-Lussac's law shows us the relationship between pressure and temperature without a change in volume. So our volume would remain constant. So if we don't allow the gas particles to move and to take up more space, if we increase the temperature, they're going to be moving around a lot more quickly. They're going to be bouncing off the sides of the container, and they're going to be increasing the pressure. So if we increase the temperature without a change in volume, we'll get an increase in pressure, and vice versa. So in this example, we have We're being asked to determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 degrees Celsius to 30 degrees Celsius. So our P1 is 1.0 atmospheres. Our T1 is 20 degrees Celsius. We're going to add 273 to that, so we get 293 degrees Kelvin. Our T2 is 30 degrees. We're going to add 273, so we get 303 degrees Kelvin. And we're being asked for the pressure. So our formula is P1 over T1 equals P2 over T2. And that formula rearranged would look like this. And then we can put our information in. So we have 1 atmosphere, 300 Kelvin, 303 Kelvin over 293 Kelvin. So our kelvins will cancel. We get a pressure in atmospheres, and that is 1.03 atm. So not a huge change in pressure, but it does go up. And really, we've only increased the temperature of the gas by 10 degrees Celsius. And really, those are fairly ambient temperatures at 20 degrees Celsius and 30 degrees Celsius. So that makes sense. Our next gas law is the combined gas law. So we combine all of those other gas laws into one. And so this formula will actually allow you to get all of the other gas laws, because normally things are constant. So if we have a constant temperature, say, we would omit the temperature from the bottom, and we would just have P1V1 equals P2V2, which is Boyles Law. And we can get all of the other equations the same way. So if the volume is constant, then we have P1 over T1 equals P2 over T2. And if the pressure is constant, we have V1 over T1 equals V2 over T2. So we have the other 3 gas laws that we just looked at. So let's look at an example. We have a sample of carbon dioxide. Doesn't really matter what the gas is, so you're going to notice that a lot of times these questions will just throw in extra information that you don't actually need. So it's saying a sample of CO2 occupies a volume of 25 liters when the pressure is 125 kilopascals and the temperature is 25 degrees Celsius. So those are our initial volumes or our initial amount. So we get V1 equals 25 liters. P1 equals 125 kilopascals. T1 is 25 degrees Celsius plus 273, so 298 degrees Kelvin. It's asking us to calculate the volume, so we're looking for V2, by the same quantity of carbon dioxide at STP. So here's where we have to remember that standard temperature and pressure means that our pressure is 101.325 kilopascals, so that's a constant value, and our temperature is 0 degrees Celsius or 273 degrees Kelvin. So we need to remember that about STP and sometimes SATP, which gives us 101 kilopascals and 298 degrees Kelvin. So our formula is P1V1 over T1 equals P2V2 over T2. So I will go through how to rearrange this. When I do this, I like to cross multiply to get rid of my fractions first, because I know lots of people don't like to see fractions. They get all scared. So if we do that cross multiplying, we now no longer have fractions. We want to isolate V2, so we're going to divide both sides by P2 and T1, and that gets us our formula rearranged. So this is going to be the formula that we are going to use. And you can rearrange all the formulas using cross multiplication. So I'm just going to go to a clean sheet so that I've got a little bit more. So we have V2 equals, so I'm going to start putting my information in. So I have 125 kilopascals, 25 liters, 273 degrees Kelvin over 101.325 kilopascals times 298 degrees Kelvin. So our kelvins cancel, our kPAs cancel, so that's how we end up with our unit for liters, and we get 28.3 liters. So that's our new volume. So that concludes reviewing the 4 gas laws. So there are going to be other videos for the ideal gas law and for gas law stoichiometry, so make sure you check those out as you move through the unit. The biggest thing to remember is don't forget to convert to degrees Kelvin. If you forget kelvins, you are not going to get the right answers.